Look up at the night sky. See the stars move across the sky. The moon and the sun do the same thing. They rise and set. It's not surprising that ancient peoples viewed the earth as fixed, and all celestial objects revolved around us. The ancient Greeks, such as Plato, Aristotle, and culminating in Ptolemy, constructed a cosmology with the earth surrounded by a number of celestial spheres that rotated around the earth each day. There was a sphere for the moon, one for the sun, one for each planet, and one for all the fixed stars. Planets were identified as different from stars because they changed their position over time, whereas the stars were seen to be eternally fixed in place. The Earth-centric model stood the test of time for over 1,500 years. It wasn't until the 16th century that things started to change when Nicholas Copernicus proposed to put the sun at the center of the solar system. In so doing, he put the Earth into rotational motion about an axis, and he put the Earth into revolutionary motion around the sun. But putting the Earth into motion was hard to swallow for most people. Copernicus's idea didn't really start to take hold until the early 17th century, when considerable evidence for the Copernican model was compiled by the likes of Tycho Brahe, Johannes Kepler, and Galileo Galilei. Tycho Brahe, with mural quadrants, sextants, and his naked eye, used parallax measurements to find distances to the planets. He focused on Mars and tabulated volumes of data on a daily basis. Using this information, Kepler found that the orbits of the planets, including the Earth, were ellipses. And Galileo, using the newly invented telescope, discovered that the Milky Way cloud was actually stars, that the sun had spots on it that indicated that the sun was rotating, that Venus has phases like the moon, indicating that it goes around the sun, and Jupiter has 4 moons. Imagine how it must have felt when Galileo first saw these moons. All the world believed that everything revolved around the Earth, and here you are looking at moons that are orbiting Jupiter, not the Earth. But resistance to change is strong, and it wasn't until the 18th century that Newton turned the tide for good. We are all familiar with his formula that force equals mass times acceleration. Newton's better understanding of gravity was the key. A good way to view gravity is to think of it as a gravitational field surrounding the object. The intrinsic strength of the field is set by the fixed mass of the object. But as you can see in this illustration, when distance from the object increases, the surface area over which the field is spread increases as well. This effectively weakens the force of gravity felt at the more distant point. We know that the geometry for a sphere has the increase in surface area proportional to the square of the radius. So the gravitational field strength is reduced by a factor of 4 every time the distance increases by a factor of 2. We call this the inverse square rule. We'll see this rule again when we discuss standard candles in our section on stars. It's interesting to note that the constant of proportionality, g, in Newton's universal gravitation formula was not known to Newton. It took another 100 years before physicists had instruments sensitive enough to measure this number. But once we had it, it became possible to measure the mass of the Earth at 6,600,000 trillion tons. Newton broke Aristotle's 2,000-year-old dictum that there are 2 sets of rules for nature. One set for here on Earth, and another set for the heavens. With Newton, we came to understand that there is only one set, and it applies everywhere. In 1752, the French astronomers Lalande and Lacaille used the parallax method to calculate the distance to the moon. Here's how it works. 1. Draw a line from a point on Earth to the moon directly overhead. 2. Extend this line to a distant star. 3. From a measured distance across the Earth, draw another line to the distant star, and another one to the moon. Measure the angle between these two lines. In our example, it's approximately 1 degree. This is the parallax. Note that this line to the moon crosses two parallel lines drawn out to the distant star. From simple geometry, we know that the parallax angle theta is also the angle between the two lines at the moon. Now we have all the angles of the Earth-Moon triangle, and we know the length of one side. Simple geometry gives us the rest. Our parallax calculation gives us 226,467 miles to the moon. Of course, the moon travels in an elliptical orbit around the Earth, so its distance varies. Here's how different full moons look between the closest and furthest points. An interesting note on distance is that once you know the distance, there are a number of other things we can learn about an object. For example, given the distance r and the angular displacement of the object in the sky, we can calculate its size. Here we see the moon's diameter is 2,174 miles. Here we are, on the surface of Mars. Mars is the furthest planet from the Sun, where a person can actually find dry land to stand on. This is the photograph taken by Curiosity that's currently roaming around the surface of Mars, digging into the surface, looking for water, past signs of life. It's April 2013, about midday, and the temperature is just about freezing. In a few hours, it'll drop to 100 below. So, I better go find some shelter. Given the orbits of Mars and the Earth are ellipses, and their total velocities are different, the distance between the two can vary from 34 to 250 million miles. Back in 2003, the two planets reached a near minimum distance of 35 million miles. The last time that they were that close was over 50,000 years ago. Rather than list all the ranges of distances between the Earth and the various planets, a good way to report planetary distance is to use an average distance from the Sun. For Mars, it's 142 million miles. Mercury, a hot cratered rock, not much bigger than the Moon, is only 36 million miles from the Sun. Venus, with its sulfuric acid atmosphere and surface temperatures that can melt lead, is 67 million miles from the Sun. Jupiter, the largest planet by far, is 483 million miles from the Sun. We'll come back to Jupiter in a minute. Saturn, with its beautiful rings, is 886 million miles from the Sun. Uranus, with its extremely cold hydrogen and helium atmosphere, is 1.78 billion miles from the Sun. Neptune, a veritable twin of Uranus, is the furthest planet from the Sun at 2.79 billion miles. Pluto, as with other dwarf planets, is in the Kuiper Belt at 3.66 billion miles from the Sun. Let's take a closer look at Jupiter. It is the giant solar system vacuum cleaner, eating up the Sun's early debris to become larger than all the rest of the planets combined. An example of this was the comet Shoemaker-Levy colliding with Jupiter in 1994. The first impact occurred on July 16th, when fragment A of the nucleus entered Jupiter's southern hemisphere at a speed of 37 miles per second. Instruments on the nearby Galileo spacecraft